different cases of the equation of change of temperature. So case one. If we are dealing, if we're using the Fourier's law of heat conduction, so when Fourier's law of heat conduction is used, then we will write the gradient of Q will now equal to the gradient of what? The gradient of K, the thermal conductivity, times the gradient of temperature. Okay, or we will say it's going to be equal to K with the Laplacian of temperature. Okay, if the thermal conductivity is a constant. Okay, and then in case 2, if the Newton's law of viscosity is applied, so if we applied Newton's law of viscosity, excuse me, Newton's law of viscosity, then we have the dot product between the shear stress tensor with the gradient of velocity, which is the the increase of thermal energy due to viscous dissipation. This will now become what? Will now become mu V plus nu times psi of mu. And you can refer this to chapter 3.3 in BSL. 3.3 number 3. Okay. So let's take a look at some more common versions or restricted versions. So as we mentioned before, actually viscous dissipation typically are not significant in most chemical process. So in more, common cases, or we should say this would be a more restricted version, you would have first, the Fourier law applies. The Fourier's law applies. And second, we will omit viscous dissipation term. Remember that viscous dissipation is important only in flows with enormous velocity gradients. Okay, and if we do that, we will now be even more converged to more restricted cases. So let's say if the fluid of interest is an ideal gas, what happens then? So for ideal gas, we know that the partial derivative of density with respect to temperature here at constant pressure will equal to -1. Okay? And so if that's the case, our equation of change of temperature becomes the following, right? So if we go back to the equation of change, now this term here becomes -1. So, and if we omit viscous dissipation, then the equation of change of temperature becomes rho Cp, substantial derivative of temperature, now equals to the Laplacian of temperature multiplied by the thermal conductivity plus the substantial derivative of pressure. Okay? And we can also write this in another form. Depending on your situation, we can also write this as rho constant volume heat capacity, so this would be the internal energy term only, equals to K Laplacian of temperature minus P times the gradient of velocity. And why is that? Because we know that Cp equals to Cv. That's for ideal gas. Now let's look at even more simplified cases. So let's say if the system has constant pressure, so full constant pressure systems, full constant, I can't write, constant pressure systems, we know that the substantial derivative of pressure over time would be 0. So the equation becomes very simple. It would be rho Cp substantial derivative of temperature equals to K times the Laplacian of temperature. Now, finally, for a constant density fluid, so constant density fluids, we now have the partial natural log of density over temperature becomes 0, right? Because it's constant. So again, the terms for the substantial derivative of pressure drops out. You get to the same equation of rho Cp dt substantial derivative of temperature now equals to K times Laplacian of temperature. So also just thermal conductivity. So it's basically showing what? Showing that the convective transport equals to conduction. Okay. And finally, we have for stationary solids. For stationary solid, we have the velocity term equals to 0. And because the velocity term equals to 0, we again have rho Cp dt equals to K times Laplacian of t. Okay? Okay, so we have the, the simplified cases discussed here. And at the last, we will have a brief discussion on what happens if we have free convection, typically, in particular. Okay? So let's take a look at the Bosonic equation of motion for forced and free convection. The Bosonic equation of motion for forced and free convection. So first, let's take a look at the Bosnick's approximation. We actually talked about this in our previous discussion on free convection and shell balance. So let's kind of, review that. So the Bosnick approximation. The Bosnick approximation. Basically, it's a Taylor series expansion. It's basically a Taylor series expansion. Expansion. So we have the density of the fluid as a function of temperature, and it will be some some density at some reference state, which were the Taylor series being expanded of, minus rho bar, and this is the coefficient of buoyant forces, and times T minus the reference temperature T bar. Here, beta bar equals to negative 1 over rho times partial rho partial T at constant pressure. And it's evaluated at T equals T bar. Okay, so what we're going to do here is we are going to substitute this equation into the equation of change of motion. Okay? So we are going to substitute rho of T into equation of change of motion. Maybe we should just specify this for free convection, because we're only dealing with free convection at the moment. And if you do that, if you substitute it into the equation of motion, you have rho d v dt equals to negative of gradient of pressure times rho g. So these are external forces, pressure and external forces, at the reference state minus rho, the gradient of the shear stress tensor, minus rho g beta times T. So that's just a additional add-on to what happens, how do we deal with free convection, under non-isothermal systems. And here is the equation of motion for free convection. Okay, finally, we will kind of, 1 second. 请进. Okay, so finally, to end the brief introduction of the equation of changes for non-isothermal systems, we'll present the general kind of like a strategy to use the equation of changes to solve steady-state problems. Okay, so we'll write that down. So the last part would be use of the equations of change to solve steady state problems. Okay, so to describe a non-isothermal flow of a Newtonian fluid, here are the steps that we need to follow through. So to describe non-isothermal flow of a Newtonian fluid, the first step is to write down three equations of changes, namely the equation of continuity, which is very simple. It's just partial rho partial t equals the negative gradient of rho v. Second would be the equation of motion, which is rho substantial derivative of velocity equals to the negative gradient of pressure minus the negative gradient, the gradient of the shear stress tensor plus rho g. Okay, the gravitational force. And finally would be the equation of energy, or we call it equation of temperature, equation of change of temperature, which we have rho Cp substantial derivative of temperature equals to negative gradient of the conductive flux minus partial natural log rho partial natural log T at constant pressure, the substantial derivative of pressure, and finally the viscous dissipation term, which is generally omitted. We should probably just point this out. Usually omitted. Okay, and with the three equation of changes, we also need equation of states. So we can really complete solving these differential equations. So we need two equation of state. One is the thermo equation of state. The pressure is a function of rho and T, for example. And then we also need the caloric equation of state, which are like the constant heat capacity, constant pressure heat capacity, which is also a function of rho and T. Things like that. Okay, so let's try to go through this rather complicated derivation again. So let's start from the beginning. I want to go through the steps just to make sure you have at least the direction ideas corrected, or figured out. So again, why are we trying to get the equation of changes for a non-isothermal system? It is because we are interested in deriving the most useful form of the energy equation, which is one that has energy or temperature in it. One that has temperature in it. Temperature appears, right? And we start by doing the energy balance, the most generic energy balance. Okay, so you have the change in energy on the left-hand side over time, and then you have the combined energy flux vector associated with the fluids, and also you would have an external, an additional term of energy coming from external forces. So then we expand the combined energy flux vector. Okay, and then we get to this point where we have everything expanded here. Okay, so we have convective transport, conduction, we have work by pressure, by viscous force, and external forces. And then because we are most interested in the temperature, right? So if you look at the left-hand side, it is the internal energy that actually has the temperature within the equation of state, okay? So we decide to try to get rid of the mechanical energy part. And actually from fluid mechanics, we actually know that the equation of mechanical energy is written as below down here. So we can actually subtract the equation, the energy balance equation, with the equation of mechanical energy, so that we come to this point, okay? So that we come to that the equation of change of internal energy. Okay, so get the equation of internal energy here, which still has the convective transport part, has conduction, but now the works associated are now going to be just what? Just going to be the reversible work by compression and viscous dissipation that's non-reversible or irreversible. Okay. So we have, greatly simplified the equation already from the energy balance to the equation of internal energy. Then we try to further simplify the equation using the idea of substantial derivative, plus the idea of thermodynamics, or from thermodynamics we know that the relation between internal energy and enthalpy, they're related by the PV work, right? So you see that in the equation of internal energy, we do have internal energy and PV term here, right? So let me underline that. We do have the internal energy term and the PV term. So the PV term and internal energy term, in principle, should be able to be coupled into the enthalpy term, okay? So the next part, we're just trying to, combine these two terms and re-represent the equation with the enthalpy. Okay, so that's what we're doing here. So we're basically going through all these steps, looking at the substantial derivative of the enthalpy and pressure, and try to come up with a relation. Okay, and finally we come to this relation down here, okay, which tells us that the substantial derivative of enthalpy equals the substantial derivative of the internal energy plus the substantial derivative of pressure plus the PV work here, okay? So you can see that in this derived relation, these two terms were already presented in the equation of internal energy. So we can substitute these two terms by the enthalpy and the pressure term. Okay, so our original equation of internal energy now becomes an equation of enthalpy. Now, I think there's a mistake here. So let me try to erase this pressure term so don't confuse ourselves. And then we know that for Newtonian fluids, the enthalpy is actually can be related, is a function of both pressure and temperature, and can be expanded as the following down here. So if we substitute this relation back to our equation, that's where we cross out the substantial derivative per pressure. And then we come to our next form of equation down here. And then we say that for most cases in chemical engineering, the viscous dissipation is typically very small. So we can actually, in most cases, omit the viscous dissipation term. Okay, so finally we have the equation of change of temperature in terms of conduction and viscous dissipation, which can be omitted typically. And for the conduction term, we can apply Fourier's law of heat conduction. So it becomes a Laplacian of temperature multiplied by the thermal conductivity. if we apply the Newton's law of viscosity, then we have this relation written down here. Okay? So, as I mentioned, for Chem E, problems, typically viscous dissipation can be omitted. So we have a most generic form for ideal gas written down here without the viscous dissipation term. And because it's ideal gas, the partial derivative of the density with respect to temperature would be -1. And then for constant pressure systems, the substantial derivative of pressure would be 0. So we have an even more simplified representation, which is just relating the change in enthalpy by the change in the thermal conduction. Okay, and for constant density fluids also, this term becomes 0, having the same form of just 2 terms. And also for stationary solids, we also have the simple representation down here. Okay, and finally, so this basically ends our discussion, right? So let's kind of write down the steps for you first. So we start by first the energy balance. And from energy balance, we have subtracted the equation of mechanical energy to get to our second result, which is the equation of internal energy. And then what we did is using the relation of substantial derivative equal to partial T plus V dot gradient operator. And then we use the thermodynamics, which is rho H equals rho U plus P, to get to our third part, which is the equation of, let's say, enthalpy. And from that, we further use the equation of states, which is H equals Cp, let's say dH dt equals to D equals to Cp dt dt, to finally get to our equation of change of temperature, which is typically rho Cp dt dt equals to negative gradient of thermal conduction, and you may have viscous dissipation. It's the dot product of the stress tensor with the velocity gradient, and maybe you will also, and then you will also have the pressure term. So you have the natural log rho natural log T at constant P substantial derivative dP dt. And we would use the Fourier law of heat conduction such that Q equals to negative K gradient of T. And typically we omit viscous dissipation, and then we look at special cases where the last term can be or cannot be omitted. Okay, and following that, we take a brief look at the Bostonic equation, especially the Bostonic equation of motion, especially for free convection scenarios. And basically, the Bostonic approximation is down here. Basically, it's just a Taylor series expansion of the density as a function of temperature with some reference temperature. Okay? And so basically, we would just plug in this relation to the equation of change, so the equation of change of motion, to get the equation of change of motion in free convection scenarios. Okay, and finally, so to actually solve a steady state problem using equation of changes, the typical standard technique would be we will write down the three equation of changes. So conservation of mass from equation of continuity, conservation of momentum for equation of motion, and conservation of energy from the equation of energy. Okay, and to actually solve for all three, we would need some equation of state, like the thermal equation of state and the caloric equation of state. Okay, so let's, in our first brief discussion about the equation of states of non-isothermal system here,